sent already, but if you want to check it, no, not that. I think the technical is in the okay, okay. Genau, ich könnte noch was. Gehen wir noch 3 Minuten, weil wir gesagt haben, um 14:20 Uhr machen wir weiter. Ah ja. Und dann kündige ich mich kurz an. Ich sage auch ein, 2 Worte.
So, I think we are all again in here, so I want to start with the afternoon session. First of all, I hope every one of you enjoyed lunch and you had a coffee, so you have enough energy for the session in the afternoon. We're going to have some interesting presentations focused on sensor systems. But before we want to start, I want to say some words about myself, why I'm here. My name is Johannes Griegler from the Technical University of Munich. And I think it's 1.5 years ago when we first had contact with Professor Fortunato and Professor Demir. And we didn't imagine to make such an event within 1.5 years with, I think, almost 100 participants here in person and more than 400 participants online. So we are very happy to be here. And I'm looking forward to the presentations now in the afternoon. We already heard some interesting applications in the morning, like fuel cells, batteries, electrical engines. And one important piece in the puzzle to have a cost-efficient production is sensor systems, because they enable us to inline do quality monitoring, but also to use data methods for improving processes. And our first speaker, Jens Reiser from Prezitec, will give us a first insight into sensor systems. The stage is yours.
So thank you very much. My name is Jens Reiser from Prezitec, and I'm going to talk about I'm not going to talk about. Okay. Then I will switch I've heard that the University of Bologna is the oldest university in Europe. So congratulations, and congratulations to Bologna, and it's a great honor to be here. Thank you for having me. Oh, by the way, I just saw that my 15 minutes are already running. Okay. Here we go. So, the title of my presentation is Going Green, Laser Welding and Sensor Technology is Driving E-Mobility, and this is the content of my talk. I will start with an introduction, then I will show you smart sensors. These sensors are then incorporated in our optics, smart optics, and finally I will sum up my talk. So allow me a short introduction. Who are we? Who is PreZitech? PreZitech is laser cutting, laser welding, and the optical measurements with two headquarters, one in Gaggenau in Germany and one in Neu-Isenburg, close to Frankfurt in Germany. And we are an independent, family-owned enterprise. The company belongs to Ms. Hartung, Mr. Versburg, and Mr. Bauer is completing the management board. Worldwide, we have about 700 employees, 300 in Gaggenau, 100 in Neu-Isenburg, and more than 200 patents. In this slide, you can see our subsidiaries. These subsidiaries are worldwide, ranging from the US via Europe up to Asia. And in particular, in the field of e-mobility, Asia was and is a big market, but now Europe is coming slowly up step by step. And in my group, we focus on e-mobility, and here we have 5 sections. These are the battery production. These batteries are then welded to modules. We focus on inverter and welding with green laser sources and high voltage electronics. We have the starter production and hairpin welding. And finally, 5th section, the fuel cell production and welding of bipolar plates. So these are the 5 sections, and we adapt our products to fit the needs of these markets. And these were 5 sections, and these are our 3 pillars of products, starting here at the left-hand side with cutting. Here you can use fixed optics for cutting thin foils in a coil-to-coil approach. In this video in the middle, you can see laser welding in our application lab here with the green laser source, for example, for welding collector foils to the tab. And finally, the 3rd pillar is the optical measurement, as shown here, contactless with light, to measure dimensions of a stator. And you can also think about to measure the deterioration of calendar rolls. Well, that said, I want to switch to our sensors more deeply and start with a sensor for welding monitoring. Again, a picture from my application lab where this sensor is mounted here at a third-party scanner optic. And if you perform welding here at the bottom, the process emissions are going back into the optics, finding their way up to this sensor here. And the sensor signals are then transferred into a voltage going to our PC and software. And here you can see the sensor in a magnification. Inside there are 3 photodiodes for different ranges of the wavelengths, and we capture here the emission, we capture and record the process light. Now seeing this sensor in action can be seen in this video here. So at the first you can see the photodiode which is sensitive in the visible range of light, and the second the photodiode which is sensitive in the near infrared. And if the current sensor signal highlighted here in blue is between the limits, the envelopes, then we say it's a good weld. If it was found to be outside, as shown here, outside the limits, then we give information to the PLC in real time saying, pay attention, there was something wrong. So a system and a sensor based on comparison. Now, how does this sensor work and what can it detect and what can it not detect? So what are here the limits? And here we perform the weld with infrared in copper, and you can see the three sensor signals, diode 1 visible, diode 2 near infrared, diode 3 which is sensitive of the wavelengths of your laser source, and finally we can also track the laser power, and this was a good weld, everything is in between the green envelopes. Now we intentionally apply defects such as a decrease of laser power. So here we have an intentionally decrease of laser power. This means infrared is not coupling into copper. It is severely back reflected. And here we get high signals on our photodiode, which is sensitive of the wavelengths of your laser source, as can be seen here. And the moment the incoupling takes place, the back reflecting signal is going back into normals in between the references. So we can see the incoupling event of infrared in copper, which might be of interest in the field of hairpin welding. Next intentionally applied defect is a gap. If you have a gap between two sheets, the temperature just cannot flow fast enough from the upper to the lower sheet, and there's a tendency that temperature increases on the upper sheet. We can see this temperature increase by an increase of the photodiode signal, which is sensitive in the near-infrared wavelengths. This is how we detect gaps. And finally, pollution. If you weld here over, in this case, intentionally applied dilution, you get a burning event, and this burning event is emitting light in the visible range. So this is how this sensor works in general, and now let's go into one particular case of e-mobility where a customer wanted to see if you have a good weld here for pouch cell welding, copper 0.3 millimeter, galvanically coated to aluminum, and he wanted to see if there is a gap and if this gap is bridged or not. So the wording we use here is false friend. It's an overlap eye weld, and by pure inspection with your pure eyes, you cannot see if it's a good weld or not. The question is, can we see it in the process emission? And the answer comes next. So what we've done here is a cross-section with a decreasing gap, copper to aluminum, copper on top, aluminum at the bottom. And this is what our customer has as an end-of-line visual inspection. Of course, when you're an expert, you can see differences. Of course, on the left-hand side, there's more copper, and the more you go to the right-hand side, the more aluminum appears that you can see here by color. But let's leave the in-visual inspection on the other side, and let's see if our sensor can give here the answer. So the answer is there a false friend? Yes or no? And what does our sensor say? When there's no electrical contact, our sensor signals rise. As soon as the gap is bridged, our sensor signals go down. So we can see during your contacting if you have an electrical contact, yes or no. And this applies for a variety of application. And the smaller the spot size, the higher the ability of such a false friend to occur. And we can have here a customer benefit. Now, a second topic frequently asked from our customers is the detection of spatters. And to be honest, we performed here a very bad weld in copper with infrared, so really defocused to have here severe spatter events. And what you will now see is at the bottom a video, a camera image, where you can see the keyhole, the white dot is the keyhole, and the photodiode signal here of the photodiode, which is sensitive in the field of near infrared. And what you can see here is that each time when a sputter event takes place, a peak in our photodiodes occur. And if you have a sputter event in copper, then we can clearly see this in the photodiode sensitive in near infrared. If you have a sputter event in aluminum, then we can see it in the photodiode sensitive in the visible range of light. For example, here, this is the keyhole, this is the sputter corresponding to this peak. This is the keyhole severely deteriorated after the sputter event corresponding to these peaks. Well, enough about this sensor for welding monitoring. By the way, have I mentioned the name? Laser Welding Monitor, LWM? If I forgot. Let's come to a next type of sensor, widespread in the field of e-mobility, a sensor for optical measurement. Here we have two sensors. One sensor here, one sensor there, working with distance, so no tactile measurement, in a coil-to-coil approach. One sensor at the bottom, one sensor at top, which can measure your thicknesses and can measure you edge and start-stop quality. And not only after calendering and in the dry condition, but also in the wet condition and also on the NMC side. We can measure thickness of coating, cutting, burn, inspection, deterioration of calendar rolls. And here we have a video how this is used in this coil-to-coil approach on this portal, moving from the left to the right, giving you the information on, in this example, graphite coating on copper, and we make a calibration when moving from left to right to give you here distance information. Another example, which is frequently asked, is here in the field of starter production. Here, customer want to know about the thickness of the insulation layer. They use this information to adapt the following not striping process, but afterwards the bending process. If they know the thickness, they adapt their bending process of the pins. And here we made a cross-section of one of these different 6 pins, where we ended up at a total thickness of 130 microns plus 30 microns, so 160 microns in total of this insulation layer. And the question is, can we measure this with our optical sensors? And the result comes next. Indeed, we can. We have this 160 microns as a geometrical thickness. We multiply this by the breaking index of the material, which is the factor 1.8, and then end up at the optical thickness of 288. And this is what can seen be here. This is the first peak between 250 and 300, and the other peaks here correspond if we make a measurement via OCT going over a mirror. So these were just 2 examples where sensors of optical measurement are interesting for customers in the field of cell production, thickness and edge measurement, and here copper coating thickness measurement. Well, this was then one sensor for laser welding. Second sensor, for example, based on the optical coherent technology for thickness measurement. We now incorporate everything into one of our optics, and this can be seen here next. Optic we call SCANMASTER. If we have a closer look, then you can see here on the right-hand side a camera, next to the camera the laser welding monitor introduced before, and next to it here the OCT technology for distance measurement. And the only taking home message here for you is we measure the distance before welding, the distance to your samples, to your batteries, and give the information to the motorized collimator. So we have here a closed loop between measurement to your samples and readjustment of the focus of your system. This may sometimes be beneficial in the field of battery contacting. Well, by this, I want to sum up my talk. I started with smart sensors and a sensor for monitoring these process emissions. I've shown you how we can detect gaps, how we can detect laser power variation and pollution. I had the example with a false friend. How we can see in the LWM signals if there's an electrical contact, yes or no. And I've shown you sputter events. Then we talked about the optical measurement, thickness of coating, thickness of hairpins, and finally we incorporate everything into the SCANMASTER with OCT sensor, LWM camera combined with a motorized collimator, laser power module based on theta technology. So we think we are ready here for Industry 4.0, inline quality control, transparency, and traceability. Thank you for your kind attention.
Thank you very much, Mr. Reiser. Thank you also for being perfectly in time and almost perfectly in time. And thank you for the interesting insights into sensor systems. I'm quite sure we're going to have some questions here or also in the online stream. Over there.
Thank you very much for your time and congratulations for the presentation. Let's say that my main question is related with the false friends identification. So it's in the daily life, all the tuning of the monitoring is done on defects that we want to identify during the process. But one important aspect from my point of view is identification of false friends. So it's I'm detecting a fault that is not a fault actually. So what's your vision on this problem and how you are trying to solve it in the daily life?
Could you just repeat your question? So you're interested in the false friend detection?
Yes.
And what exactly was your question?
So what's the strategy that you are applying to identify a false friend? So an error that actually is not an error.
So what we do here with our sensor is to tell the customer, you do have electrical contact, so there is a gap, but the gap is bridged, and there is a gap, and this gap is not bridged. And the later is what we call false friend. Just by visual inspection, the weld looks good, but it is not. There is no electrical contact. And our sensor helps here to detect this. Was this an appropriate answer to your question? Then let's meet in a coffee break.
We have one more question in the fourth row here.
In which range is your wavelength range is the NIR sensor working for detection of the false friend, for example?
This might depend on the application. We were able to see false friend on copper to aluminum, copper to hilumine, thick aluminum to thick thick aluminum to thick aluminum. So for all three types of contacting, pouch cells, cylindrical cells, copper to aluminum, and prismatic cells, aluminum to aluminum, we were able to see it.
No, my question is something different.
Huh?
The wavelengths.
Yeah. This depends on the application.
Yeah.
So there are.
But the problem is that you are limited by the glass observation, and therefore the best range is not available. The ideal range is not available. What is your compromise?
So the examples I've just told you were experimentally done in my application lab, and we were able to detect this by our sensors. We have 3 photodiodes, and depending on the application, we use photodiode 1 or photodiode 2 or photodiode 3.
No answer.
Yes.
I think we can answer this question maybe in the coffee break in more detail. Thank you, Mr. Reiser, for the nice presentation. I think the sensor system we are talking about now in the next presentation was already mentioned today, I think also in the last presentation. Mr. Steinbrecht from Lessmüller will tell us a little bit about the OCT sensor.
Okay, thank you. Warm welcome to everybody on this nice afternoon. Thank you for the opportunity to present our technologies. And we are the smart people who let the others work. This means the guys that we've heard in the morning, the laser manufacturers, they weld, and we only tell after the weld whether they have done their job good or not. So I start with a slide that is already 2 years old, and I showed that 2 years ago. What is our motivation at all the e-mobility? What's really behind it? This is from 2019, and there we see everybody was already talking about that this would be the future, but it was a mere less than 10% of the cars, of the new cars in Europe with batteries, traction batteries inside. But this has dramatically changed, and if we look at the latest figures from last year, we already have close to 40% cars with either full battery or hybrids or plug-in hybrids. This means the future is what we've heard today is already arrived. This is all in production. Again, a lot of the figures have been heard today. This is older figures that people say, experts say that the production capacity of batteries will quadruple up to 1.3 terawatt hours per year in 2030. This means small companies, or not even small companies, will become those gigafactories. Can you hear me from this side as well? In large industrial entities. And again, Tesla tops it by telling that they alone will have 3 terawatt hours by 2030. I tried to bring down those 3 terawatt hours into cars. If we have a car and an average battery of 80 kilowatt hours, this means 37 million cars per year. This is what they're talking about, capacity. And if we bring that down to single batteries, and I start with the well-known 18650, still used, this would mean more than 240 billion batteries. You say this is outdated? Yes, but there's a new one, the 4680. This still means more than 30 billion batteries per year. That's why we've heard that there's an upcoming shortage of materials and production capacity. Let's bring that down to the single vehicle again. And again, I take my 80 kilowatt hours car. Of the small batteries, there were typically 6,500 batteries. The 2170, which is used in Tesla Y model, is still 4,500. And the latest, you still need close to 1,000 batteries per car. And the good news is I'm a laser guy as well, a lot of the applications will be done by laser. And you have a minimum 2 times the connections than you have the number of batteries, because you have 2 poles, so you need at least 2 welds. But in reality, you need more. So this means still for the latest type, we need about 2,000 connections per car. And all of those should be good ones. And the laser itself is a very stable process, as we know, but you still have influencers like the laser power can vary, the beam quality can vary. Our optics are not perfect. You have focus shift, you have contamination of the optics, you have the part itself that may vary in geometry, the clamping. Clamping is an always underestimated influencer. You have the materials, the alloys that may change. You have the surface, depending on your pre-processes that varies. You have pollution during the pre-processes. And your motion system may vary in speed, may vary in positioning. This all means you need process monitoring. You need process control in order, or at least you need quality assurance. You have to get good welds, and that's our task. We've seen this slide before, all the applications. I don't have to remind you about that. We are doing all of this. Just a short definition before I continue with my more detailed talk. Pre, in, and post. Obviously, pre means everything that we do before the welding. In red, it's hot. We always do the process monitoring, whether it's keyhole measurement or measuring the process emissions. And green is the color of hope, and we hope that the seam is good when we're finished. This means seam inspection. Always is green in my talks. Application, we have seen all of these today, and we've seen from Coherent the arm laser, which makes a perfect weld, but if it's not positioned properly, the best laser won't help you to improve the quality. You need the positioning as soon as your part has tolerances in clamping and part. So OCT is one tool for seam tracking. OCT is also a tool for the depth measurement, and I will show you a little sample later on. And then the process monitoring, some call it LWM, we call it weld check. All my predecessors just said about LWM also is valid for our weld check. Thanks to Trumpf, you can see how our OCT works. We have the OCT scanner, where the blue light is the OCT scanner, collinear inflected to the red main beam. We have 2 scanners, and with those 2 scanners, we can move our measurement scan lines around the TCP in order to do seam tracking, or in order to do seam inspection after the weld, or we can look into the keyhole. Let's have one first application for seam tracking. This is something that we've seen today already in one talk with the camera. We can do the same. We want to acknowledge the position of here the battery, and we just make some short scans, because these 4 scans would identify the position and the rotation of the part. And then with the next sequential thing, before we start weld, we make another OCT weld directly in front of the laser beam, and this we guide, we do the seam tracking in front of the hot welding. And this looks like this. You have the scan line. This is 160 times slower than in reality. You see the pilot laser that would indicate the weld laser, and we just follow exactly the path around the battery in order to ensure the right position of the beam on the part. So if the cell is finished, we have bus bar welding or can cap connections, and again we can use various tools. The OCT can identify holes very easily. You make 3 scans, so you have 3 points, and 3 points identify the center and the radius of a circle, and then you can reposition your welding path according to the hole that has been punched. Again, we can do depth measurement for connections and bus bar welding. We can do process monitoring with the weld check, or we can do seam inspection after the welding, and this can be seen in we have a live demonstration for post-processing in the other room. So step by and we can show you how this works in reality. And now we're coming to another real application. Again, you see, seems like everybody has a Trump scanner today. You can see the Trump scanner. You can see the upcollimation, and this is the OCT. OCT scanner. So this is all that you need for pre, in, and post measurement. In this application, which is battery welding for Mercedes, the first step that we do, we make one short scan across the clamping in order to identify the clamping edges, and then we reposition the beam exactly in the middle of the clamping in order not to weld the clamping onto the part, but to be in the middle. The next short scan line is along the seam in order to find the focus position. We measure the focus, and then we can either, depending on the machine setup, we can either give a go or no go to the welding, or we can send a corrective value, and then you can change the focus by either changing the upcollimation or moving a lens or moving the whole optics. So these 2 steps each step takes about 50 milliseconds. This means within 100 milliseconds you have already ensured that you're welding at the right position, in the right focus position. And then we are looking, during the welding, we look into the keyhole. The keyhole typically is, has a certain shape, and this shape depends on speed, power, and material. We're not measuring the welding depth, we're measuring the lowest point of the keyhole, which typically is a little bit less than the penetration itself, because you have the heat affected zone. Second, the lowest point is not in the middle of your laser spot, but it's slightly behind, and that's why we can position with our OCT scanner, we can position the measurement point slightly behind the real welding laser. This is a real sample where copper is welded onto aluminum, and you can see where we have measured, slightly behind the TCP, and we have, you see all the black dots are the measurement points, and the art now is to find the right algorithms to really measure the lowest point. The problem is the keyhole is highly reflective. The keyhole is nothing stable. It's always moving around and changes its shape all the time. So we have to find the algorithms and identify the values that really represent the lowest point. And here you can see that on the right there is a weld where the laser power has been ramped up, and below you see the longitudinal cut and etching, and you see the red points indicating the measurement values, and you see the blue line which indicates the percentile filter with the algorithms, and you see that you really can measure the depth. It's collinear, and you have a congruence between the etching and the measurement on the material and the OCT measurement. So now we have the batteries connected. Now we need the packaging, and packaging meanwhile tends, first you had modules that you put into packages and the packages into the cars, but the next generation the modules will be packed into the car, directly into the car chassis, or the batteries will be packed into that. So a lot of the applications there are like body in white applications where you again need seam tracking because you want tight seams, you need depth measurement in order not to penetrate too much into the battery or into whatever. So we can also work if you have material combinations, what we've heard today, where you need assist wire. We still have our WELDING camera-based system that identifies the wire, the position of the process, and then looks at the final result. And we can do seam inspection with OCT running over the part and looking for, like you see here, the black holes, looking for failures in the seam. So this is a three-dimensional display of a measurement. If you have sufficient time, you can do it like that. If you don't have sufficient time, you take one scan line along the seam, and then you already can identify splashes, pores, debris, and whatever. So if you like OCT, and if you like to have an OCT, and you're afraid that your optics will not work with the OCT, you have good chances that it will work. So we have already more than 100 units out in the field, and we have done the combination with remote optics from ScanLab, from Hayek, from Trump, from Fanuc, and others are coming up. If you say, oh, I don't want to weld remote, I have fixed optics. Fixed optics typically is easier because you have consistent optical properties that makes life easier in any way. Come to us. We're in the other booth. We have a little booth there, and we have our live system. Come and visit us. In September, we're downtown Munich, 300 meters away from the Oktoberfest. So that's always a good chance to come and visit us. Thank you.
Thank you very much, Mr. Steinbrecht. Thank you also for the invitation for the Oktoberfest. I think maybe some of the people will come and join us.
For you, it's easy.
Hopefully it's going to happen, no? So, do we have questions for Mr. Steinbrecht? Over here.
Thank you for the interesting presentation. I have a question. You were saying that you are measuring the penetration just behind the laser beam. But if you are not welding in a straight line, but for example you are wobbling or making different shapes, how are you adjusting the position of the reading if you are continuously changing the position of the laser? Are you preloading somewhere the path?
We have one solution where we control both scanners. We control the welding scanner and we control our OCT scanner simultaneously. This is not via field bus, but this is a faster interconnection, and then we can really follow, even when we wobble, we can follow the wobble curve. But this needs a very fast interface between the OCT scanner and the main scanner. If you don't have that fast one, you need the different technology.
Do we have more questions? In the almost last row.
Thank you once again for the presentation. In case we have a lap join weld, in case you have a lap join weld, so two material one above the other, are you to detect a gap between the two interface?
If we can't measure the lower one, yes, for the identification of a false friend is a problem. There are some results and approaches to that, but we have no solution yet for the false friend.
And one more question over there.
Thank you very much for the presentation. My name is Harald Toll from Enlight. I'm wondering if you are able to detect not false friend, but a gap between the sheets, over even in a overlapped joint, especially for example an aluminum combination, and to do it both in and post process in the same time, because aluminum, we know it because of the keyhole, there are a few problems to detect the depth of the seam.
Well, typically we can do seam tracking and in, or seam tracking and seam inspection simultaneously. At the moment, depending on the complexity of the keyhole measurement, we are not able to do the seam inspection synchronously. The good news is with the second run, if you have the time, with the second run you could also measure the finalized, the solidified seam, but then you need more cycle time.
More cycle time. Thank you very much.
Thank you, Mr. Steinbrecht, for the presentation and answering the questions. And we'll see us later. So the next presentation is from Rayleigh's about scanning units and monitoring systems. Unfortunately, the original speaker, Mr. Jan-Bernd Habedank, can't be here with us today. But we have Mr. Lehmann. He's happy to answer the questions, and Mr. Habedank, he recorded his talk, so we can listen to him in an online presentation and afterwards do a Q&A with you.
So, a warm hello to everyone in this room, and as Mr. Grigler said, regrettably my colleague Jan Habedank can't be here because of an infection with the virus, and we decided to record a video of his presentation, and I hope the presentation finds your interest, and I will be available for questions afterwards. Thank you.
Okay, good afternoon, everybody, and welcome to my presentation on how pre-focusing deflection units from relays enable e-mobility applications and optimize process monitoring. My name is Jan Habedank. I'm the head of the TCC, the Technical Competence Center at Relays. We are a group of engineers and physicists who do the application at the customer side, but also do the support if something is not working and enable you to keep your machines running. Unfortunately, I cannot be here in person today. This is due to a positive COVID test that I took this morning. I'm still okay. I don't have strong symptoms, but it would not be okay to join the conference under these circumstances, of course. Which is quite sad because I was very excited for the conference and meet you all, but it has to be this way. I'm in my hotel room now, looking at my positive tests and bring you my presentation this way. So my plan for today is to start with a very brief introduction into relays, then explain the principle of pre-focusing laser deflection units, and talk about some advantages they have for process monitoring. Then mention a few software and control features that we offer dedicated for e-mobility, and close with a few application examples from our customers and a brief summary. So Relays is based in Wesseling, Germany. We're about 140 people. Most of them are in Wesseling, where we also have our R&D, but we also do have a large office in China, where we have production for the local market, and a small office, a small sales office in the United States. We do not define ourselves by our markets that we cover, because they are very, very diverse, from solar to textile to e-mobility, but rather by the key applications that we cover with our products and solutions. And these are additive manufacturing, cutting and perforating, marking and surface processing, and welding. And as you can see, the lower three are applications that you need all the time in electric mobility for many, many applications. Additive manufacturing, maybe not so much, but this is a hype of its own. So for us, e-mobility is currently the fastest growing market for relays, not only in Asia, where, of course, over the last decade already, e-mobility has grown tremendously, but also in Europe and the United States. And this is not only due to the exploding electrification trend in general, we believe, but also due to the substitution of conventional processes like ultrasonic welding or resistant spot welding or mechanical punching by laser processes, because they are more flexible, they are without any tool wear, and they are very fast. And this gives many, many advantages in production, and these two overlapping trends basically result in the increase in demand that we see. Just quickly, the products and solutions that we offer. We have our 2-axis laser deflection units, or scanners, as you may know them, which basically consist of 2 galvo motors which turn 2 mirrors. So the laser beam is deflected in a certain processing field. The focusing here is performed by an f-theta lens, which you do not see here because the bottom side is open. So this f-theta lens is basically attached to the bottom of the scanner and focuses the laser beam. So here we have a post-focusing unit, basically, because the laser beam is focused after the deflection, after the mirrors. In contrast to that, we have our pre-focusing laser deflection units. Here, the focusing is performed before the deflection by the mirrors, but I will talk about that in detail a little bit later because this is the topic of my talk. So I will stop here at this point. Additionally, we offer software and controls. So we have our operating software RayGuide, and we have our SPICE3 control card, which basically communicates to the entire machine, to the entire system. So it communicates to the laser and also communicates to the scanner and synchronizes them. The fourth field is the market of scan field calibration, which we are just about to enter right now. We are about to introduce a new product at Laser World of Photonics in Munich in April, which is called the Scan Field Calibrator, which is a device with which you can calibrate your scan field down to a few micrometer precision in a very large working space. So we're talking about 600 by 600 square millimeters working fields, and you can reach precisions in the magnitude of 10 microns here, or maybe even below that. And this is very important when it comes to additive manufacturing, but also to e-mobility applications, where we see increasing demand in precision when it comes to scan field calibration. I will not talk about this during my presentation here. If you do have any questions, feel free to reach out, contact me or any of my colleagues at Raylays. We'll provide you with more information on that product. Now I would like to focus on the pre-focusing laser deflection units. And first of all, explain the operating principle. You can see it on the right. We have a laser beam that's coming into the scanner. In this case, via a QBH socket with an integrated collimator. So the collimated beam enters the scanner and reaches a Z lens. And this Z lens is moving and expands the beam before it reaches the so-called F lens, which focuses then the beam before it reaches the mirrors. The mirrors then perform the deflection in the field, and the moving Z lens is there in order to compensate for the difference in the optical path that is covered by the laser. Of course, it's a different way that if you want to operate in the corner of the scan field compared to the middle. So this is why the Z lens moves, and the F lens focuses the laser beam before it reaches the mirrors. We don't have an f-theta lens here. Only protection windows which seal the housing from below. This operating principle, this pre-focusing principle, has a few key benefits that I would like to address here. First of all, you have a very small spot size in a very large field, which is typically not achievable with f-theta lenses, or easily achievable with f-theta lenses, because these lenses would have to be very large, very big, very carefully machined, and then they are very, very expensive. We can reach these small spots, let's say magnitude of 50 micrometers in a field of 500, for example, of course, depending on the wavelength and the laser beam parameters, but these types of spot sizes in very large fields. We have a very simple and secure installation process due to the integrated collimator and the fiber coupling. So you basically just plug in the fiber and you're ready to go. Moreover, you have a quick exchange protective window in the bottom. basically you have two windows. You have an inner protection window, which seals the housing permanently, and this cannot easily be removed by a customer. And then you have an outer protection window, and this is just a clip-on system, so you can remove it and replace it within a matter of seconds, so your production is not stopped. The entire system, so the entire deflection unit, is IP64 dust protected and manufactured in a clean room. So quality issues due to burn-ins, etc., are a thing of the past here. And you have a process light output without lens aberrations. And this is the key point that I want to address in my remaining talk here. Because as you can see, the process light that comes back from the processing zone is reflected by the mirrors and then hits this dichroic element without having passed any lens. And this is a great advantage of this construction principle compared to theta-based systems, because if you have your process light first pass through an theta lens, the different wavelengths that the process light and also the image, basically also in the visible wavelength, the different wavelengths are refracted in a different angle by the theta lens. So they are split up basically, and it's very tricky to evaluate them with a sensor, such as a camera or a pyrometer, etc. Additionally, the monitoring wavelengths also of a pyrometer, for example, here displayed in green, which can be coupled into the scanner, are not refracted in a different manner by any type of lens compared to the laser beam. The effect is that the pyrometer spot, so your sensor spot, and the laser spot perfectly match each other and are not in a different area in the processing field, which you would have if you were using an theta lens here. So these fundamental construction principle advantages enable process monitoring, or are the basis for a simple and easy and error-free process monitoring system. For this, we offer an additional unit, which we call the array spectre, which is basically this box that you can see here, which attaches to the AS fiber. And in this unit, you have an additional moving lens if you want to mount a camera. And this moving lens compensates again for the difference in the optical path length and enables you to get high contrast images in the entire field. You can add all kinds of cameras. We are not fixed or stuck with one manufacturer here, as long as they match certain mechanical and sensor-related specifications. Additionally, to camera monitoring, we have another process light output here, where you can attach sensors. As mentioned before, a pyrometer, for example, pyrometer, or other welding inspection systems, for example, an Precitech LWM, or a process observer, or a weld watcher, or any other diode-based systems. And this, again, without any lens aberrations that you would have in theta-based systems. We offer these scanners in different apertures. We have the AS Fiber 50, as you can see on the left, with the very large mirrors for very small spots in very large fields. And we have the AS Fiber 30 for the more dynamic applications, because you have smaller mirrors and you can move them faster. The great thing about these are that you can arrange them very closely together, so they can operate in a common field, in a unified field. For example, as displayed here in the quadruple arrangement, seen from below, you can see the windows basically where the laser beams come out of, and you can arrange them in a 4x4, 2x2 arrangement. So, for example, in additive manufacturing, you can parallelize your jobs, but also in e-mobility, you can parallelize your welding or your cutting job, which is great for efficiency. In terms of software and controls, we offer a wide variety of features which are dedicated for e-mobility. Of course, they can be used also for other markets, but for example, we have multi-scan field support for increased efficiency and throughput. And our customers use this for electrode cutting, for example, and also welding. We have marking on the fly for belt speed compensation, also in acceleration and deceleration phases, because the correction of the geometry that the scanner has to move happens on the card and happens very quickly. We have welding ramp functions if you want to avoid spatter, for example, in the welding of battery cases. We have different wobble shapes, Lissajous figures, and all of these are made to provide a very stable melting pool without a lot of spatter. We're able to record feedback signals from the scanner, so you have the information about temperatures, etc. And we are able to record or to change the power dependent on the speed that the scanner is operating at and the position where it's at. So if you, for example, have a corner and you have to decelerate your scanner, or your mirrors, the effect would be, without this speed and position dependent power control, that you have a burn-in or something because the laser power is constant. If you can correct that, you can keep the laser energy constant during the process to ensure the process quality. Now I want to move on to some application examples where these pre-focusing systems are in use. And I want to start off by an application which we are currently developing with a partner, with a customer, called Sonplas, also a company based in Bavaria, who are currently developing a machine for the cutting of electrodes, of battery electrodes, which is able to do roll-to-roll notching, but also roll-to-sheet separation, and also roll-to-stack separation, where you basically reduce another process, a handling process, between cutting and stacking. They developed a specific laser process that ensures very good cutting edge quality with very, very low heat affected zone, as you can see on the right here, with the images of the laser cut NMC cathodes and the laser cut graphite anodes. And again, here we are operating in a very large field and still achieve a very small spot size and a very high cutting speed. And this combination is only possible if you go into the pre-focusing direction, because in a normal 2D scanning, you wouldn't be able to achieve these large fields. Another very important application for us is the welding of bipolar plates for fuel cells. We see that this process is becoming the state of the art for large bipolar plates for the fuel cell stacks, especially for the PEM fuel cell stacks, where you have an overlap welding of two stainless steel sheets that have to be welded together. The requirements are very high here. The joints have to be gas tight in order to well, not have the hydrogen and oxygen leave the fuel cell, basically. And what we see is that once these systems and these machines enter the mass market and fuel cells are produced on a large scale, process monitoring will play a very important role here to gain information about the weld seam quality here. If you have any holes, if you have any false friends where you don't have a contact, for example, you can see these defects with the state-of-the-art sensors that I mentioned before. But the deflection unit that you need also has to provide the basis, basically, to record these signals. On the right here, you can see an AS Fiber 50, so the large one, integrated in a machine at Dana Reins, who are producing bipolar plates here and welding them together in order to manufacture fuel cell stacks. So these systems are in use, and they do a great job of producing these very, very fine and very precise weld seams that have to be introduced here. Last but not least, we have the large field of contacting of batteries, of bus bars, any current conducting elements that you have in the battery storage systems. There's such a wide variety that there's definitely not the one process that can be used for everything. You have different materials, you have different thicknesses, you have different requirements in terms of the currents that need to be transmitted over these contacts. And you mostly have dissimilar materials which introduce intermetallic phases. So this poses a great challenge. Also, we see a trend towards higher currents over the contacts because the batteries tend to get larger. You see the Tesla cells, for example, they increase in size, but also other manufacturers tend to build larger cells, so the currents increase, which again increases the requirements for the joints, for the welding joints. At the same time, we have a trend towards decreasing thickness of housing components to increase energy density. It's basically just dead weight, and you want to reduce that. And this, combined with the high currents, poses very challenging requirements towards the process, because we want to avoid increased aging due to heat introduction into the battery cell, for example, and we want to ensure a long-term reliability of the contacts. And all of these challenges basically lead to the necessity to precisely adjust and monitor your process. You have probably a very small process window that you are in, and you need to monitor that. And therefore, the pre-focusing systems are the ideal basis in order to recall the process and gain information about its quality. To summarize my talk, we see that pre-focusing laser deflection units gain enormous traction in the e-mobility market due to the exploding market in general, but also the substitution of conventional processes. Simple, flexible, and aberration-free process monitoring with cameras and other sensors is the key, or will be the key, to successful production in the future. And pre-focusing deflection units form the ideal basis for that. They are currently already used in cell manufacturing and battery production, all the way from the level of the electrode to the level of the storage system, in many cutting and welding applications, and also in cleaning applications, by the way. Cleaning is also very important. Aside from the battery, we see that bipolar plates and fuel cells gain importance and will gain importance, especially if you consider the current developments regarding natural gas. We will probably see an increasing dependence on hydrogen in the future. And this is why we do consider fuel cells as a very important part in the future energy economy. And they have to be produced. And again, you will need very small spots and large processing fields to manufacture these systems. And with this, I would like to close. I thank you very much for your attention. Again, I am sorry that I couldn't be here in person. I would have liked to go into a discussion right now. If you do have any questions, here are my contacts. Feel free to ask me. I will try to answer them as good as possible or pass them forward to one of our colleagues. Again, thank you very much for your attention, and I wish you a great workshop.
Thank you very much, Mr. Habedank. I'm very happy that in times of COVID, we find solutions like this, that we can record such a presentation in a very short amount of time. And I'm very happy that we have Mr. Lehmann here to answer some of your questions. I at least read one question in the online chat. It's concerning the limitation in terms of dynamics of the set lens. So the question is, does the set lens limit the dynamics in comparison to an f-theta lens?
So this is a very good question. It can limit the dynamics in certain applications when it comes to diagonal applications in the working field, but in most cases it cannot limit the dynamic of the mirrors. And we have developed a special dynamic set or focus system that even provides more dynamic behavior, as you know it from standard galvo systems for future applications.
Thank you very much. I think that answers the question. Do we have more questions from the auditorium? Gökhan.
So, thank you all for the presentation. I mean, we find ways also in the last minute. So, thanks to Jan as well. I wish we could have met him. So, my question regards a little bit about the outlook on scanning systems, because there are some applications in which today, strangely, we find enough laser power, and the scanner speed has to be. People tend to go towards very, very quick scanning speeds. We're speaking about tens of meters per second and so on. And we spoke about the dynamics as well. It's a generic question about how Rayleigh sees the scanning speed levels with the precision that we can still maintain. So, or maybe are we going back to the polygonal scanners for some applications? Are you looking into these? Because we do some basic calculations, the numbers that we see, we freak out. We say that that's not possible with a mechanical mirror. So how far do you think you will push with the dynamics in terms of speed?
So, I mean, what's possible today are very, very high speeds, and it really depends on the application we are talking about, because in the meanwhile, we have so-called tunings. Tuning is the digital electronic control of the galvos, and this can be optimized for all applications. And for example, for solar wafers, we have a tuning with 200 rad per second. That means with an f-theta lens of 250 millimeters, we are reaching a speed of 50 meter per second in this field size. And this is really a lot. And this is, let's say, on the lower edge, a polygon scanner can do. But of course, there are other application needs where you have a lot of corners in and whatever, then you need another tuning. But at the end of the day, the speed and the dynamics of the mirrors together with the digital control is very, very high. But to be honest, we don't reach the speed of a polygon scanner, but polygon scanner has got another disadvantages. I hope this answered the questions.
Thank you. I don't see another question, so I say thank you, Mr. Lehmann, for answering the questions.
Thank you very much.
And please tell Mr. Habedank we are very sorry he couldn't be here today, and we hope he's going to be all right soon. I will tell him. Thank you. Perfect. So now we come to the last presentation for today. It's connected to inline production monitoring. And my Italian is a little rusty. I still try to pronounce the name properly. Let's welcome Mr. Luca Porcelluzzi from MKS Instruments, and have fun with your presentation.
Many thanks. So also for Italian, it's not easy to spelling my surname. Don't worry.
I gave my best.
No, you did great. So welcome. Last presentation before coffee break. So hope to enjoy you. And I will try to stay on the topic of my presentation, that is monitoring, and with absolute reading and measurement of battery welding, because during my colleague's presentation, I understand that there's a lot of topics already on the field, like which laser is best for which material and speeds and others. So we can speak of this for very, very long time, but let's go. Okay, I put the summary on the top, just to give you what is the real difference here is understanding of the parameters, understanding of the variable, and the measurement can be achieved in the laser process. Know and correctly understand the performance of the parameter and the system let you drive to a better system, to a better process, to more value on your job. So in this time also restore the system to a previous setup or to develop a new setup that is slightly different from the previous one. It's something that must pass through some data, some information that let you to have the correct understanding on where is your sample, where is your material, how your laser is going through. So we are now start to speak about photonics dimension, photonics information, not more mechanical or electrical. I have to keep it this. So at the end, the quality of the process, the value of the parts produced is higher when you know correctly your system. So, and my presentation from Photonic Division in MKS Instruments will try to this. Well, maintenance is already mentioned, but is something that goes subsidiary of this. So when you know your system, you know also how to keep it at the best performance. So just an overview on MKS. We are a supplier worldwide for a lot of system and application in photonics, but also in semiconductor. And actually, we have more than 1,000 scientists in R&D in developing new instruments for the future, I will tell you. That's a lot of also in our division. In this presentation, we are going to speak more in details about lasers, so power reading and propagation of the lasers. So the energy we have in our system to make our process, because we have to understand this. Okay, so that is our mission. We're also thinking that always that if you don't know our parameter, we cannot improve it. So just give you a short overlook on what is our system, what we are talking about. We are talking about a system that is already patented, it's already on a state of the art since 2014, and now is declining in this integrated version. So we have an all-in-one, I will use that one, sorry. All-in-one beam profiling system that is a passing through system. There's nothing that's eat your beam, so we have no limit of the power. And then we put a power reader, a power sensor here that is water cooled. You can imagine we are talking about a several kilowatt laser system in this moment. All of this is built to stay in production line. The KPI, the key parameter indicator, I told you, laser power, spot size, waist position, waist side, parameter of the propagation like M square, divergence, and so on. For what this is good, I will highlight it here, long and short time measurements, because you can install and use it for a very quick understand or a pass-fail between each job measurement session, or you can use it for long-run session because you have a fail and you want to investigate deeper what's going wrong. Just a spot on the accuracy before to go through to two application case that we will present. We tested and we already submitted this application, this white paper, sorry, and the accuracy is about 3.5% of any other beam profiler system at state of the art. So let's go. This is the software. So this is the standalone software. So it's not the integrated one, but you can imagine you can integrate this device in any PLC, in any machine. But just to give you the correct understanding of what we will show later. Beam images and manual cursor, so let you investigate what is the real laser on your system, what is going on. This is a camera that's collected the images longitudinally, and you can see this. Then you can have the marker that keep you tracking the waist location, the focal shift, and other data. Results, absolutely. Display and acoustic measurement is, can be see this, but most important is the graph, the chart possibility. So you can chart over the time all the data you see in the results tab. So, and this let you to have in the real time when application is so fast, like we spoke all today. In real time, you need something that's collected data. Could be a log, and you can investigate later, or could be also visual in this case, and you can have a very fast pass-fail check on this. Okay, 3D display, and so on. Just to conclude the presentation of the device, it's the capability to stay in the production. As I told you, it can be mounted upside down, vertical, horizontal, doesn't matter, because there's nothing that's be hurted there. The important is to stay in the right position, close to your machine, to work in the right moment, and to collect the data for you. Well, as was requested, to stay on the technical side, we go for two case studies. First one, a general battery welding inspection. You saw a lot of this before, so just a system presentation. So we will speak in this and in the second case about a 2 kilowatt single mode fiber laser, a gantry, 3-axis gantry, and just a point on the difference between the 2 focal length and the waste expected, because this is something that is nominal, is the theoretically expected beam propagation, delivery 100 micron spot in the waste, and with this focal length. Well, the application, the task, was in this case to collect information to give the correct data. Like I show you. This is what is expected on the application. So it's expected to deliver 100 micron spot size. You can imagine all the picture you saw from the first presentation, from the previous presentation. Here is your hairpin, is a bus, or whatever you have to weld there. But generally, you want to have this 20 megawatts square centimeter, or about that. Because you make your calculus, you select your lasers, you select your optics, and so on and so forth. Well, what happens? That is 2 kilowatt relatively clean protective glass. We use this word just because it's not possible to say it's absolutely clean or not clean, but you have this information. What happens? That's the measurements give you that the real waste is just up here, still about 100 micron, so not so far away, but you see that your density, power density is increased. We go up to 27 megawatts square centimeter. Could be good, could be not. Let's see what happens in the welding process, but what happens, that's when we change this condition, what happens when we have a dirty protective glass? So we collect measurements that here is the process, is the working plane, okay? The waste is up here. So at the process, we pass from a desired 20 megawatt square centimeter to a 3 megawatt, order of magnitude less. And the waste goes up due to the focal shift, thermal effect that any laser submitted, and about 10 millimeters, okay? See at the land, the graph over the time of the focal shift. So it's the moving of the waste from this point up, okay? And well, averaging the astigmatism here, you can see that's what I saw before, that you have about 1 order of magnitude less on the power density, and also the sorry, also the diameter of your process increase for more or less 100%, because we expect 100, we have 200, okay, micron. And this is for just the dust and two-hold protective window, okay? So the information from this first inspection give a really clear procedure. So maintenance to change or clean the protective window before the welding, because this measurement will be done in every part produced. So every job, for just a couple of seconds, you see 7 seconds is enough to check all of these parameters, and you decide if you have to follow and make your job, or you stop by and keep it, maintenance the machine. Okay. This also gives us a nice information that maybe any of you is already aware, but is that's the single mode fiber laser is less affected than the focus shift, and this is something to know. And this liked to the customer so much that submitted us the second case, and we go to a very troubleshooting case where the next machine have a slightly different, but more or less is comparable. So we have a longer focal length and smaller waste spot, okay? The problem here was well addressed already. You can see it's a loss of penetration and welding test failure, so the part produced was bad. So wasting money, wasting time, and so on. Okay, the customer and our researcher make some investigation, and the focus shift is too much for the system. What we measured is very too much. And also the procedure in maintenance was have some lack in the time to intervene. So this is give you very fast the information. This was before. This is what we investigate. We put the instruments in the machine, and this is what happens. So we have, this is the working plane, and the waste goes up here, and I will resume the data, the information right here. So look at this number. We are talking about 7 millimeters and an increase of about 100% of the spot diameter in a few seconds when we work not at the maximum power of the system, but roughly operational power. So this drives us to the conclusion that there are some components also in the machine that is not correct selected. And with the better investigation and selection, we reduce this focus shift. You see this is the new acquisition, and the data assumed is here. So we can reduce more or less half of the focus shift and the dimension spread over the working plane, using this on every single job. That is for remind you that is important to thinking in the process, not waste material, and we can do it very fast. And this is absolute data. This millimeter, micrometer, what we are talking here is absolute, and it's not a relative measurement. We can provide a NIST traceable performance calibration certificate for any our devices. And this led you already to stay in the industry 4.0, just to give you a hint on this. Well, this is my last slide. So, any question?
Thank you very much for the interesting presentation. Do we have questions? We have one in the back row.
So thank you very much for the interesting presentation. My question would be, what are the do you have some limitation on, let's say, the emission mode of the laser beam that you require during the measurement? So do you need to have a continuous wave laser beam, or can it be any type of pulse wave laser beam that we've been saying in the various applications? And if you have some limitations on the minimum spot size that you can actually measure.
Okay. Thank you for your question. Good question, as we used to see. The limitation of the input is not a real limitation. Just to tell you, the cameras inside the beam profiler can work in a millisecond time, just to give you an idea. The power measurements need for high power, we are talking about 1, 2, 3 kilowatts, needs at least 1, 2, 3 seconds to be asymptotically trustable. So the combination of two factors give you like, okay, you need 2-3 seconds to have a trustable measure, trustable reading. But depends, because you can also thinking to have a power reading in a separate session. That's you have more time when you load and unload the pallet from the machine or your sample, and a beam profiler investigation that is very short and can be triggered from your laser output. So if you have a millisecond modulated emission that is not CW but could be, you can work with this. You have just to synchronize your measurements with your device in the same. So it's born in CW concept, but can be drive also impulsed. It's something that is not in the data sheet, but we just to give you the second answer, the limit of the the spot size. We got good measurement set up with a femtowatt in the green for 30 micron spot in the waist. And this is really far below our working range we declare in the data sheet, but we did. So actually the potential of these instruments is to see more than seeing the near RF wavelength, so we can go in green, we can go in blue, and also the pulsed is not a nightmare anymore for us. Hope to answer to both your questions. Okay.
Perfect. Do we have more questions? Last chance for today to ask something.
Yeah.
Okay, thank you very much,
You're
Mr.
welcome.
Boccioluzzi. So, in terms of presentations, we are at the end for today. I think we heard some very valuable insights into beam sources and also sensor technology. Tomorrow at 9 a.m. in the morning, we're going to continue and go over to the end users and to the machine integrators to learn a little more about applications and challenges when integrating equipment. For today, so actually the conference or the workshop is over for all people who joined us online. We're going to meet us tomorrow at 9 a.m. For all the other people, I would like to ask Antonio Raspa to come to the stage because he's going to tell us how the discussions in the next section are going to happen.
Yes, thank you very much to invite me to be here today. Okay, what I learned, what I bring back today is that is very dynamic, this environment, and is really a fast, very fast process and environment. So what we are going to do now, just after the coffee break or during the coffee break, is to work together and to understand better the dynamics of this environment. Let's say, as with OCT, we understand where we have to position the beam to weld. It's interesting also to understand all together and to work together to understand where we position all together as industry, as technologies. So, okay, my name is Antonio Raspa. I'm working at EPIC, European Photonic Industry Consortium. Okay, this slide is already nearly to hold. Soon we will represent 800 members in all the segments of photonics, so from lasers to quantum technologies, optics, and so on. Just shortly, what is EPIC? EPIC is made by this fantastic team of 13, 14 persons. We support the technology, we support the ecosystem, and really we would like to do the best for this European ecosystem. So, what is photonics in Europe? This is the data coming from the latest report from Photonics 21, the report made by Thematis. It's interesting that Industry 4.0, where this is the segment that is including laser processing, is 19% of the overall turnover of Europe. And going through the data, industrial laser manufacturing processes is 13.5 billion euro. And these are the data of 2019. So this is, I think, is a good reason to work and also to work together. So, as I said, I would like to understand, I would like that we try to understand the dynamics of this environment and especially the dynamics, the future dynamics of laser processes for e-mobility. In parallel with the coffee break, in the same room or in a room nearby, we will brainstorm on 4 selected teams in 4 working groups. The time is from 16:10 until 17:20, so a little more, yes, 1 hour, a little more than 1 hour. And then we try to wrap up also the results of these 4 working groups. So at least by 17:30 we will have the result of this discussion among us. As I said, we selected with the organization of this event 4 themes. The first theme is how can laser be further integrated into interconnected production systems and lines? So what is necessary to do from the point of view of the lasers and ancillary systems? Another interesting point maybe is what are the opportunities and the challenges of laser processes for hydrogen fuel cells. This is another emerging technologies. Also, what are the innovative, the future combination of material and laser processes that we foreseen, that we envisage? Last point is also what are the potential roles of laser processes in conjunction with other methods for energy production, storage, and delivery in electrical vehicles. So somehow we are trying to create in this room 4 crystal balls, and we try to imagine our future and also to understand where we are going. So I wait for you after the coffee break. So take the coffee, don't relax too much, because then we will work all together on these 4 topics.
Thank you, Mr. Raspa. I would say we might postpone it to 4:15 to start with the discussion, because we are a little bit delayed. So please be again here in like 20 minutes and enjoy your coffee.